Okay, so this is the second of the L'Hopital's worksheet number 2, the free response one that we're going to do with you. But remember, you still need to have all the work shown and do it along with us, or put your video on pause, try it yourself, do it in pencil, and then come back and watch and fix the things that maybe you didn't do so perfect on, or if there's like a notation thing, fix your notation. I mean, the idea is once you've seen one, they all have the same kind of general flow. So we have our graph that's on our board so that it has a big graph that we can kind of refer back to. And the stem of the problem says, let G be the function defined on the closed interval from -2 to 4. The graph of G consisting of 3 line segments is shown to the left. So it's kind of like a little weird. You have this portion of a diagonal line. You don't really know where that's kind of going through, but we do have a point marked at 1,4 and then a point at -2, 0. Kind of this decreasing portion of a diagonal line, and then you have another one, but it's at a different rate of change. We have a point at 2, 1, and then a point at 4, -1. So that's our graph of G, and we are going from -2 to 4 on that closed interval. So all that looks great. And then it says, let f be the function given by the integral defined function f of x equals the definite integral from 2 to x of g of t dt. And Mr. Harding just reminded me as we were writing this problem on the board, man, we haven't really done one where the boundaries have been flipped for a while. Sometimes that happens in a part of our problem, and you have to negate it. And we haven't done one where it hasn't just been a single variable up here, where it would be the second issue of fundamental theorem of calculus, where you would have to do chain rule. So we kind of haven't had that yet, but that, remember, are things that can happen. So this is just a two-parter, part A and part B. So part A says to find the limit as x approaches 4 of sine of pi over 2x all over f of x. So if we have a limit approaching a constant, the first thing we're going to try to do is direct substitution. But now, since we kind of have that idea that, hey, sometimes that 0 over 0, we can't finagle. I mean, what would we do if it was 0 over 0 here? This is function notation. This is just sine of one thing. Like, we better test it and see. So if we test this one, the limit as x approaches 4 of sine of pi over 2x over f of x, and we try to just plug in 4, we would have sine of pi over 2 times 4 over f of 4. Well, pi over 2 times 4, what would that do? That would reduce to 2 pi, and sine of 2 pi, well, that's an exact value you're supposed to know. So 2 pi is the same as where 0 radians would be on our unit circle, and the ordered pair there is 1, 0, and sine of that would be 0. So this would be going to 0. And we're not going to string it with the equal sign and say 0 in the numerator. We're just going to kind of write it down. F of 4. Oh, well, we have that integral defined function, right? For f of x. So f of 4, which I have to do a little scratch work on, would equal the definite integral from 2 to 4. I'm just replacing the x on both sides with that value of 4 of g of t dt. So we want to know on our g graph, how much area do we accumulate from 2 to 4? Well, if this is 2, 1, we have a height of 1, a base of 1, triangles above the x-axis, 1/2, 1 times 1 would be 1/2. But then now we have a base of 1, a height of -1, or you're thinking you're below the x-axis. So this would also be 1/2, 1 times 1, but it would be negative, and wouldn't they cancel? Or you can see the symmetry there and go, oh yeah, that's going to be a 0 as well. So 0 over 0 means try to finagle, but there's no algebra to do. And now if there's no algebra to do, we can bust out L'Hopital's. So we've shown our test for why it's going to work, and then we're going to say that we're using it. So we like the L'Hopital's way. The other way is actually like this. I got to look at it. Let's see. So I make sure I spell it right. Where it's more French. L'Hopital's that way. So just so that you're exposed to that. So if we're going to use L'Hopital's rule, then we want to take the derivative of the top, take the derivative of the bottom, because this is one of our 3 different indeterminate options where L'Hopital's is going to work. And the limit as x approaches 4 of this original problem should be the same thing as the limit as x approaches 4 of the derivative of each part. So the limit as x approaches 4 You guys be careful when you're taking the derivative, right? The derivative sign, we're doing derivatives as cosine of the inside, leaving it unchanged, but it's not just a single x, so isn't it chain rule? So it'd be multiplied by the derivative inside, which would be pi over 2. So if I put that pi over 2 in front, it would be pi over 2 times cosine of pi over 2x. And of course, if you left the pi over 2 at the end, it's not going to matter. Multiplication is commutative, and you can multiply in any order. The derivative of the bottom is just going to turn into f prime of x in function notation. And now I'm ready to substitute in my c value. So when we substitute, that's where the word limit goes away. So we would have pi over 2 times cosine of pi over 2 times 4 all over f prime of 4. I'm right at the edge of the board. And then I'm just going to draw an arrow to say, okay, what this leads to. So the pi over 2 times 4, again, we have a little reducing, will give us 2 pi. Well, I just showed my unit circle right here. So the cosine of 2 pi is 1. And now I have pi over 2 times 1. And I evaluated that exact value over f prime of 4. Oh, well, I don't know what f prime is, but we have an integral defined function about f. And if we take the derivative of both sides by fundamental theorem of calculus, f prime of x would be the derivative of the antiderivative is just the function with that upper boundary replaced in here. Oh, so f prime of x is really g of x by that duh part of fundamental theorem of calculus. So this graph, which is the graph of g, is really the graph of f prime. So if I want to know what f prime of 4 is, I really just want the output at 4, which was one of the points they marked for us. So the output at 4 was -1, and pi over 2 times 1 would just stay pi over 2. And divided by -1 will give us negative pi over 2. So there's part A. Okay. So hopefully now you're like getting the hang of it. Your notation's getting better. Where you're trying to test it, just don't string it with that equal 0 over 0 because they don't like that. And I think you would lose the points that you could possibly earn. And there's not going to be a ton of points probably awarded to this anyway. So you don't want to lose any of the points on notation. Okay. So now we are ready for the next part. This, like I said, was only a part A and a part B. So part B says, let h, they're just plopping in a new function for us. Let h of x be defined by h of x equals f of x over x squared. And we're supposed to find h prime of 3. Well, before I can find h prime of 3, a derivative evaluated at a value, maybe we need to find h prime of x in general terms first. So that's what we're going to do. And the bigger bulk of the points, if this were actually on a free response problem, will come from finding h prime in terms of x first. And then the last point would probably be the answer when you plug in the instant of 3. So I'm taking the derivative left-hand side, h of x, when I take the derivative, turn into h prime of x. Oh, the right-hand side is Herney's favorite rule. Aren't we busting out quotient rule? So instead of singing to you, I'm just going to say it. So the bottom times the derivative of the top minus big brackets, the top times the derivative of the bottom, all over the bottom squared. So that would be what my notation looks like. And maybe we clean that up, not that you have to, but some of you might feel a little bit more comfortable if you wrote x squared times f prime of x. This is all one term. Maybe you flip the order minus 2x times f of x all over x to the 4th. Power to power, we're going to multiply those exponents. You don't have to, like I said. And now we're going to replace every x we see with a 3. So h prime of 3 equals 3 squared times f prime of 3 minus 2 times 3 times f of 3 all over 3 to the 4th power. So we have some numbers, but we don't have all numbers. So they need you to show them that you know how to find these two values. So you don't have to square 3 to give you 9. You don't have to do 3 to the 4th to give you 81. In fact, you shouldn't probably do that because if you make a dumb algebra mistake, like you guys are notorious for, you're going to lose your answer point. But we do need to pull f prime of 3 off the graph. But remember, this is the graph of f prime. It's the same thing as the graph of g. And right at 3, it looks like we have a value of 0. You don't really have to do 2 times 3 to give you 6. If you did, it would be okay, but you can't make an arithmetic mistake there. F of 3, okay, well now we maybe have to do a little bit of work. So we go back to our integral defined function. I had to do f of 4 previous in the problem, but now I gotta do f of 3. So f of 3 would be the area swept out from 2 to 3 of g of t dt. So boundaries are normal. We don't have to negate anything. 2 to 3 is above the x-axis. It's just our little triangle here, a base of 1, a height of 1, 1/2, 1 times 1 would just stay 1/2. And then I would stop. I mean, this is a homework problem that you guys are doing on a worksheet, but we're trying to mimic as much as we can the non-calculator part of a response question. So that numerically is fine. It's all numbers now. So good review of some quotient rule stuff and a little bit of chain rule here, and then L'Hopital's, of course. Last minute thoughts. Hopefully now you got the hang of it. Bust out number 2 and make sure you've written down 1 and 3 that we worked with you, and 4 and 5 are on the back for you to also do on your own, and 2 you finish on the front. All right. Talk to you later.